Have you ever really stopped to think about how you're talking to a machine? I mean, how does clicking a mouse or typing on a keyboard actually turn into something a computer can understand? How do we communicate with a piece of silicon? Well, that's what we're going to figure out. Let's crack the code on how your computer actually thinks.
So, right at the heart of so many devices we use every day, there's a tiny chip called the microcontroller. You can think of it as the brain. And it's an absolute powerhouse of calculation. But it's got one huge limitation. It only speaks a single, very, very specific language.
And this slide just perfectly captures the huge communication gap we're talking about. On the left, that's us. Human thought, logic, simple math. But on the right, that's what the computer's processor, its brain, actually sees. Just a long, endless stream of ones and zeros. It's like we're speaking two completely different languages.
Which leads us to the million-dollar question, right? How in the world do we translate our complex ideas into that super simple binary stream? How do we build a bridge to cross that massive gap?
Okay, so the heart of the problem is this. The CPU, the brain of the whole operation, only understands instructions written in binary code. To you and me, that looks like complete gibberish. But to the machine, it's the only thing that makes any sense at all.
To solve this puzzle, we desperately need a translator. And that first, most basic layer of translation comes from a special language called assembly.
The best way to think about assembly language is as the native tongue of the processor itself. Now, it's not exactly English, but believe me, it is a massive step up from a wall of ones and zeros. It takes those raw machine codes and gives them names that we humans can actually read and remember.
You know, every single assembly instruction follows a really simple, predictable structure. First, you've got the action, which has a fancy name, a mnemonic. And then you've got the things it's supposed to act on. Those are the operands. Just think of it like a super direct, no-nonsense command. Do this to that. Simple.
So what in the world is a mnemonic? It's really just a short, easy-to-remember code for a specific machine instruction. So instead of trying to memorize a crazy long string of ones and zeros for addition, we just write add D. Instead of some binary gobbledygook for moving data, we simply write MOV. It's what makes programming even possible for us humans.
Okay, so we've got our commands down, add, move, you name it. But that's really only half the puzzle, isn't it? An instruction isn't very helpful if it doesn't know what data it's supposed to add or where it's supposed to move it. We still need to give it directions.
And this is where something called addressing modes comes into the picture. You can honestly just think of them as different ways of giving directions to the CPU. They're the specific methods we use to tell an instruction exactly where to find the data it needs to do its job.
All right, the simplest method is called immediate addressing. It's like saying, hey, use the number 5. The data isn't hiding out somewhere in memory. It's literally baked right into the command itself. It's the most direct way you can possibly provide a piece of information.
So here's a real-life example. Move A #5AH. This command tells the CPU to move the value, in this case it's 5A in hexadecimal, into a little temporary storage spot on the chip called register A. Now, see that hash symbol? That's the crucial clue. It tells the processor, hey, the value you need is right here, immediately after me.
Next up, we've got direct addressing. This is less like handing someone an object and more like giving them a specific street address. You're not providing the data itself, but you're telling them the exact memory location where they can go and find it. So, a command might look something like this. MOV A, 30H. Notice what's missing. There's no hash symbol. That's the secret signal to the CPU. It means, don't use the value 30H. Instead, I want you to go to memory address 30H, see what's stored there, and move that data into register A.
And now for a slightly more clever method, indirect addressing. This is kind of like saying, I don't have the address on me, but my friend over there does. Go ask them. The command points to a register, and that register holds the real address where the data is. It's a really flexible way to do things. So in this case, the command is move A, at R0. That @ sign is the big signal for indirect addressing. It tells the CPU, okay, first, go look inside register R0. Whatever number you find in there, that's the memory address you need to go to. Then, grab the beta from that address and pop it into A.
Okay, let's take a breath. We have mnemonics that tell us the action, and we have addressing modes for finding the data. So now let's put all the pieces together and see the magic happen, how our human-friendly assembly code turns into a pure machine command.
This slide shows the whole journey, start to finish. Step 1. A programmer writes a line of code that we can actually read, something like move a #01h. Step 2. A special program called an assembler takes that line and translates it. And finally, step 3, the CPU gets the final product, the pure machine code, which in this case is 7401. The human idea has finally become the machine's language.
This really gives us the big picture of where assembly fits into the whole ecosystem. It's that absolutely critical bridge. Way up top, you have high-level languages like Python or C, which are much closer to how we think. But those languages don't talk directly to the CPU. No way. They get compiled down to assembly, which is then translated into the final binary code that the processor actually understands. Now, I know what you might be thinking. This all seems pretty low level, maybe a little old school, and you know what? You're not wrong. But that doesn't mean it isn't still incredibly important. Assembly language is a critical tool in a ton of modern technology.
So why does any of this still matter today? Well, because it gives programmers the ultimate control. Think about the tiny little chip inside your microwave or your car. Memory is super tight, so you need the insane efficiency of assembly. Or what about a high-speed trading system where every single nanosecond counts? You need the raw, unadulterated speed of assembly. And if you're writing the software that lets your computer talk to your printer, a device driver, you have to speak the hardware's native language. And that language is assembly.
So that kind of leaves us with one final thought. From your coffee maker to the systems that control the traffic lights on your way to work, this hidden language is absolutely everywhere, silently translating our needs into the binary heartbeat of machines. So what everyday device did you use today that deep down relies on this secret code to even function?